All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. We are moving right along in Unit 4, and we're actually in the very last topic of Unit 4, which means, you know what? You can start to get excited about the fact that it means we're getting close to testing. I know that's exactly what you guys wanted to hear. But in all seriousness, yeah, we're continuing to move through here and looking at aqueous reactions, types of chemical reactions. And the previous videos that you've been watching through, there was a very defined focus on metathesis reactions as well as acid-base reactions. And so now I want to revisit that third type of reaction, which is the oxidation-reduction reactions, which are commonly referred to as redox reactions. Now, this is going to cover information in Chapter 4, Section 4, but then also in Chapter 20, Sections 1 and 2. And I'm going to be splitting this topic video into two parts, so just kind of mentally prepare yourself for that. There's going to be one part that's going to be very much looking at the conceptual pieces, and then there's going to be another part where we look at some examples and some practice and some things like that. So kind of mentally prepare yourself for what that's going to look like. So as we look at this particular topic and as we talk about the types of reactions, we're going to need to define some terms. And so as we look at redox reactions, let's start there. So here we go. Oxidation and reduction reactions. So in any oxidation reduction reaction or a redox reaction, one or more electrons are being transferred from one species to the next. Okay, and this is something that is very unique to redox reactions. Redox reactions, the focus is on the transfer of electrons from one substance to another. You think about the reactions that we looked at even with metathesis or even acid-base reactions, it wasn't necessarily focusing in on a transfer of electrons. With metathesis, we were looking at precipitate formation, we were looking at formation of a weak or a non-electrolyte, we were looking at formation of a gas, and then even with acid-base reactions, we were looking at transfers of protons, right? Well, within oxidation and reduction reactions, the focus is in specifically on the electrons. So redox reactions look at the transfer of one or more electrons from one substance to another. So species, substance can be used interchangeably there. Now, within redox reactions, chemists are going to use and make use of a tool called oxidation numbers. Now, oxidation number is something that you may be familiar with. You may be thinking back to kind of this first thing that I'm listing here, the charge of an atom if it's a monatomic ion, right? And so that's this kind of idea that, you know, sodium ion, Na1+, that's its charge, its oxidation number would be +1, because that's the charge of it in that particular ion. However, in redox reactions, it's going to be based off of a hypothetical charge that's assigned using a very specific set of rules. Okay, and so as we look at redox reactions, we're going to need to focus in on that second bullet point going forward. Now, in redox reactions, it's important for us to be able to recognize that electrons are always going to move from a substance that is oxidized to a substance that is reduced. Now, that's going to lead us to want to define, can we define those terms oxidized and reduced? And so from a chemistry perspective, oxidation is more than just simply reacting with oxygen. So oxidation or oxidized simply refers to a loss of electrons by a substance. Okay, and so if you look at the particular example that I've shared with you there, I've got lithium metal that's reacting and it's changing to aqueous lithium ion plus an electron. That would represent an oxidation reaction. The solid lost an electron in that particular process. That's why the electron's a product. And then you have reduction, or something that's being reduced is something that simply gains electrons throughout a chemical process. And so if you're following along with the example that's been listed there, you've got the two iron 3+ ions and you've got those 2 electrons that are serving as a reactant, the iron 3 plus ions, each of them gain 1 of those electrons, and they get converted into 2 iron 2 plus ions. And so in that particular process, the iron 3 plus was reduced. It gained electrons. Okay, and now I have some very lovely mnemonics that you can use to help you remember these definitions. If you want to be able to remember oxidation and reduction, you can either use oil rig or Leo the lion goes grr. Now that sounds kind of ridiculous, but oil rig stands for oxidation is loss, referring to electrons, and the rig component is reduction is gained, right? So oil rig, oxidation is loss, reduction is gain. Or if you don't like oil rigs and you want to be more environmentally conscious, you could focus in on Leo the lion goes grr, right? So Leo, loss of electrons, oxidized. The lion goes grr, gain of electrons, reduced. Okay, now obviously AP is not going to test you on either of those mnemonics. I just use them because I think they're very simple and they help you quickly be able to recall kind of the difference between something that's being oxidized versus something that's being reduced. Okay, and so remember oil rig or Leo the lion goes grr. All right. Now, let's talk about oxidation numbers using that second kind of bullet point from the previous slide, right? I mentioned that there were rules that chemists use when it comes to assigning oxidation numbers to a particular compound or the elements that make up that compound, okay? And so there are some general things that we're going to need to talk about, and then we can dive into some of the specifics. So first of all, the first rule that we need to keep in mind is that if you have an atom that's in its elemental form, so let's say that you had sodium metal, just regular sodium metal, or you had hydrogen gas, right? The oxidation number of an atom in its elemental form is always 0. So if you have sodium metal, oxidation number 0. Hydrogen gas, oxidation number 0. Bromine, Br2, liquid, oxidation number 0. Okay, so elements, oxidation number 0. For your monoatomic ions, right? So let's say that you have the formation of sodium ion in a process, right? The charge of the ion is going to be equal to the oxidation number. All right, so if the charge on the ion is +1, that means that its oxidation number, if the charge is 1+, the oxidation number is +1. That's really important. I just made a distinction between +1 versus 1+. Okay. The third thing that we want to consider as we're going through and assigning oxidation numbers. Nonmetals usually have negative oxidation numbers. All right. That kind of makes sense because it kind of goes back into the charge component. However, there are things to consider. There are instances in which nonmetals can have positive oxidation states. Some things that you need to consider as rules that need to kind of be ingrained into your brain for nonmetals. First, oxygen is going to always be -2 unless it's in a peroxide or if it's bonded to fluorine, right? So oxygen's always -2 unless it's in a peroxide. So then it's going to have a -1 oxidation state. Or if it's paired with fluorine, then it's going to have a +2 oxidation state. All right. For hydrogen, hydrogen's special, right? When hydrogen is bonded to a nonmetal, it's going to take on an oxidation state that's +1. When hydrogen is bonded to a metal, like a sodium hydride, for example, the hydrogen is going to take on a -1 oxidation state. All right, the third thing that I've got listed there, the oxidation number of fluorine in all compounds is -1. So fluorine is the only substance that's a nonmetal that we can definitively say will always have a negative oxidation state. And if you think about it, it's because it's the most electronegative element on the periodic table. Now that means that other nonmetals, like we saw even with oxygen, but even some of the other nonmetals, they can have positive oxidation numbers within a compound. Okay. Then the last kind of bullet point to help drive our discussion is to talk about the sum of oxidation numbers. So if you're dealing with an ion or you're dealing with a compound, the sum of the oxidation numbers in that atom, if it's neutral, they have to add up to 0. So the oxidation states, the sum of the oxidation states should add up to 0 if the compound is neutral. If you're dealing with an ion, a polyatomic ion, for example, that means that the sum of the oxidation numbers needs to add up and equal the charge of that particular ion. Okay, hopefully that makes sense. And like I said, I'll be providing some examples for you guys to look at later in a separate video so that can help contextualize some of these rules that we're looking at. Okay. All right. Now, kind of another overarching big picture thing I want us to take away now that we understand what an oxidation reaction is. We've got this transfer of electrons. We've got this idea of how to assign oxidation numbers. We can identify what types of reactions fall under this oxidation reduction classification. And so what we find is that combination reactions, aka synthesis reactions, are oxidation and reduction. Decomposition reactions are oxidation and reduction. And combustion reactions are oxidation reduction reactions. Okay? Because in each of those reactions, there's going to be an oxidation, a change in the oxidation state of each of at least one thing in both sides of the equation. All right. And so hopefully you can see that also, which we'll see on the next slide. There will be that single replacement reactions also show instances where they are oxidation and reduction reactions. Okay. And what I might do, ladies and gentlemen, I'll produce a separate video where we go through and maybe we'll look at the oxidation states for each of these reactions that I've listed here. And so you can see how the oxidation number changes as we go from reactants to product side. I think that'll be helpful. All right. Now, within single replacement reactions, so really if you look at it, the 4 of the 5 reaction types you learned about in honors chemistry are really classified as oxidation reduction. Right? And so I've given you a general form. A plus BC produces AC plus B. Right? And so then a more specific example, you've got potassium metal plus water produces potassium hydroxide and hydrogen gas. Now, things to look for to be able to identify something as single replacement. You usually have an element that's going to replace another element that's in an aqueous solution. Now, in this particular case, it doesn't start off as aqueous, but you do have water that's present. And as you're performing single replacement reactions, always keep in mind that metals will only replace other metals in reactions. Obviously, when we're dealing with something like this where you've got potassium with water, hydrogen is the thing that's being replaced because that's the substance that will typically take on that positive oxidation state when it's interacting with oxygen. Okay, there can be instances where you have a nonmetal replacing another nonmetal. That's really going to be only with your halogens. So if you've got a reaction where you've got something like fluorine is reacting with sodium chloride, then what's going to happen is the fluorine is going to replace the chloride ions that are in sodium chloride. Right? So halogens are able to replace other halogens. And then the last thing to consider here is that when we talk about single replacement reactions, there is a possibility that no reaction can take place. And so chemists use what's known as the activity series to determine whether or not that chemical reaction will take place. And the activity series is essentially measuring how easily something can be oxidized in a given process, specifically when we're looking at the activity series of metals. All right, and so here's our last slide that we want to look at, the activity series as it pertains to oxidation. So in this table, you should notice that they've got a list of oxidation reactions that are taking place. They're showing each of those metals or each of those substances losing electrons, right? And so what they're showing you is that as you move up this table, you get an increase in oxidation. It's easier for those substances that are near the top to be oxidized. And something that I think is important to recognize is that elements that are in group 1 in general are more easily oxidized than the other elements, right? I mean, you've got within your top 5, you've got lithium, potassium, and sodium as 3 of those 5 elements that are in part of group 1, and then the others are in group 2. Now, the activity series is meant to show us whether or not metals can replace other metals in a single replacement reaction. And so the way this would work, let's say that lithium was the metal that was trying to replace, let's say, zinc in a compound, for example. Because lithium is higher up on the activity series, it's more easily oxidized, it more readily loses electrons. It's going to be able to kick out zinc from whatever compound it's in and form lithium ions and then form zinc metal. Now, obviously, the reverse would not take place. If zinc were there and you wanted zinc to replace, let's say, barium from solution, well, because zinc is lower on the activity series, zinc would not be able to react with the barium ions to displace it. It would just stay, the zinc would stay as the metal, the barium would remain as ions in solution. Okay? And so the activity series, as it relates to oxidation, it shows us and it's measuring how readily one metal oxidizes as opposed to another. So the higher up on the list, the easier it is for it to lose electrons. The lower on the list, the harder it is for it to lose electrons. Okay. Now, I hope that makes sense. This has kind of given us our big picture overview of oxidation and reduction. Hopefully this has been insightful. I think it will help. There'll be another video that's going to come out that's going to talk into the kind of more of the specifics of where we're going from here. So thank you guys for watching this. Be on the lookout for that other video, and don't forget to fill out the Google form. Ask me any questions that you have when you get done. Thank you guys. I'll see you again soon.